All right, welcome back. So we've just finished proving that the condition that we imposed on our flow is preserved. And now we are concerned with trying to show that the flow exists for all time. Eventually, we want to show that it becomes a straight line. All right, let's get into it. So uh, let's talk about. Oh, where's my. Sorry, I'm a bit blind. Road to global existence. T equals not 8, infinity. All right. Okay. So for t equals infinity, we need to control the geometry along the flow to make sure nothing bad happens. And the reason why I know that's enough is because we have the following known result. I'm going to call it a fact. Now, this fact is a theorem, and it's a theorem that has been proved in many different variations and many different situations, many different times. Basically, this is usually referred to as local existence or local well-posedness. Let me write down the statement that we'll use, and then I'll talk about it a little bit, and then we'll move on. Okay, I'm going to write it in kind of a funny way. If the maximal time of existence is finite, then there does not exist a constant. So it does not. Now let's double underline this fact. There does not exist a constant C such that the position vector and the derivative of curvature in L2 is bounded by that constant. Okay. So what this means is that if there is a constant that satisfies this equation, then we know that the maximal time of existence is infinite. And now, what is this thing? What is this? Where does this come from? So basically, our curvature flow equations are fourth order, quasi-linear, uh, degenerate parabolic equations for the position vector. So they're systems. They're systems of equations. And these are boundary value problems as well. Now, the theory of PDE is huge, massive, extensive, and I don't think anyone knows all of it, and certainly I don't know hardly any of it, but I know some of it. And it doesn't exactly cover this case completely, but you can do a certain transformation to turn it into something like a classical PDE problem. For example, what you can do is you can take your curve, whatever it may look like, and then along the curve you have your where's my little, yeah, here we go. You have your frame, your tangent vector, and your normal vector. And then what you do is you foliate the space near your curve by, now I'm just doing copy and pasting here, but you're supposed to extend in the normal direction. So you foliate it by little copies of your curve, and that gives you a parameterization of the neighborhood of your curve. And you can use this parameterization to express your differential equation as a PDE for the normal distance in that normal coordinate. And if you do that, then you'll be able to transform into this scalar equation and this vector equation back and forth. You know, you have a one-to-one map between the two. And you can apply existing PDE theory to the scalar problem, and that's going to tell you that as long as your function has sufficient regularity, has sufficient smoothness, then you are going to get a solution to your equation, and it's going to be a smooth solution, and well, it'll be smooth for positive times, and it will satisfy the vector evolution equation as we wrote them down before. So that's how you get existence. And what happens as time moves on? Well, as time moves on, some things can happen. Bad things can happen. So, for example, this representation can become invalid, or maybe the curve just drifts off to infinity. That can happen. Pretty much any bad thing that can happen is ruled out by having an estimate of the form star. So if you have star, if you have this type of estimate, then no bad thing can happen, and it just continues to exist forever. Now, you might need to readjust your coordinate system as you move forward in future, but it's possible as long as you have this estimate. So our task, our strategy, I always forget to turn that off. Our strategy is to prove an estimate of the form star. And just note that this constant can depend on the capital T, because the capital T is a finite number in this sort of clause. So it's okay as long as it depends on capital T so that it's finite for each finite T. So I'll just say that. Note that C may depend on T. It can depend on a lot of things. As long as it's finite, it's fine. And you get global existence. Now, that doesn't really tell you anything about the shape of the eventual limit. It doesn't even tell you that the eventual limit exists. It might still float off to infinity. It just tells you that if something bad does happen, it must happen very slowly in infinite time. So there's still work to be done, important work to be done, but this is the main focus of at least this section. And it's a big step. It's a big step. Okay, so what we're going to do now is something sort of inelegant but effective. We're going to use a nuclear weapon. Use a nuke. Let me not use the word nuke. We're going to use a sledgehammer. Let's use sledgehammer. My son is very interested in nuclear technologies. I think he just likes explosions anyway, so I hear him telling me about nukes all the time. Don't worry, he doesn't like nuclear weapons, but certainly likes nuclear reactors. Okay, so we're going to use the sledgehammer. So here's another fact, but this fact, I'll have a citation for it. This is the aforementioned Chuk-Kuver-Chetzler, and this will work for both the free elastic flow and the curved diffusion flow, and in fact for a lot of flows this works. It's a very powerful weapon. And okay, so what do they say? They give us an evolution equation, very strong evolution equation. You can calculate the time derivative of not just one derivative of k, but as many derivatives as you like. L2. So this is my notation right now for ddt. And what you find is that you have a diffusion term, and notice the coefficient is not 2, it's been reduced, so there's some interpolation at work here. Um, and then you have Ks, and your diffusion term is higher order. Two more derivatives on the curvature because it's a fourth order equation. And this is bounded by a constant, not exactly a constant. It can't be a constant unless we're talking about a much simpler equation. It's a constant that depends on the evolving length and the curvature in L2. And it depends on them in such a way that if the length is bounded from below and above, and curvature is bounded from above, so K bar, then this C is finite. No, you can't. Okay, that's all you need to know. Oh, and it depends on L. Sorry. It also depends on small l, script L. Okay, but the script L here is just a fixed parameter for each order of differentiation. Now this is for both in our setting. Where's my cursor? I need to make the cursor bigger. Both free elastic flow and curved diffusion flow. Okay, and more flows as well. Now, from this evolution equation, we can get quite a few very strong estimates. In particular, let's just think for a second. For curved diffusion flow, we have already that the length. Okay, so there's a very convenient fact from our setting. So we've got these. How do I think that's straight. We've got these parallel lines, and just due to the most basic considerations of the setting, we have some kind of curve between them. The length of this curve cannot be 0. It has to be at least the distance between these two lines. So this lower bound for length is free. This comes for nothing. The upper bound, yeah, let me just, I don't even need to write this, I can just talk about this. This is free for both. The upper bound for length comes for curved diffusion flow for free. Oh, sorry, you can't see this. Curved diffusion flow, it's free because it's a gradient flow for, or something like a gradient flow for length. For free elastic flow, it comes from the preservation of the total turning condition. So this is the calculation from before. So what I'll write here is free elastic flow C above. Okay. Now for the curvature in L2, for the free, the situation is kind of the same but reversed. For the free elastic flow, it's free, and for the curved diffusion flow, it's in the calculation up there, C above. So these quantities are all very well behaved under the so can I, yeah, so both of these quantities are very well behaved under the curved diffusion flow and free elastic flow given our initial assumption, and this L is just a parameter. So that means that we can apply this estimate and we can replace this constant by a genuine universal constant that's not going to blow up or change with time. Time independent constant. Now what can we also do? We can also change this term into one of these by using the Poincare inequality and Vertinger inequalities depending on whether L is even or odd. You need to use both because you need to do it twice, so that we have an ODE inequality that we can really do something with. So we change this. So we've got this term prime plus, and then there's a constant here which is going to depend on just the length, but the length is uniformly bounded from above and below, so we're good to go. And yeah, we just step down. So one thing to remember, you can always step down on the left-hand side in the derivatives and step up on the right-hand side, as long as the coefficient is positive. Okay, so we get that, and then this is by another constant. Okay, we use two hats, why not? Just hat it all up. And now you think about what this means. So you have, phi prime, I'm just going to use the same character as before, phi prime plus some constant times phi bounded by another constant, 0, 1. If phi becomes really large, okay, then the left-hand side will be bigger than C1 eventually, okay? So in particular, so it might be helpful if you think about this inequality with the, so I'll use the hats because I did that before. Minus C hat phi plus C double hat. So if this phi gets too large, then the derivative must be negative. So it must decrease. And how large can it get? Well, maximum C double hat divided by C hat. So what this gives you is a uniform estimate for this quantity. And thinking back to our constant, it really depends only on L. So we get a uniform estimate for all derivatives of curvature at any time depending only on L. Okay, and of course it depends on the initial curve, but it does not depend on time. Okay, cool. So why do I call this a sledgehammer? I call this a sledgehammer because we only really needed the derivative to be bounded, and we actually bounded everything. But it's still useful. It's very useful. And this is the power of the Chuk-Kubert-Schätzler interpolation framework. Right, so that's that. The next thing we need to do is bound the position vector, and this is a bit different. And in fact, I'm going to leave that for the next video. So next time, we're going to talk about how you bound the position vector along the flow. There's a kind of a general way and a specific way, and I'm going to do the general way, but there are specific techniques that you can use if the general way fails. But in this case, it succeeds, which is due to our sledgehammer. Okay, I'll see you next time. Thank you for your attention. All right, peace.